This chapter we get to discuss ratios and rates. A ratio is a comparison of two numbers by quantities. A ratio can be written as a fraction, so it can be simplified. For example, a ratio of 1 to 2 is, well, 1/2. A ratio of 2 to 4 is 2/4, so 1/2. Let's express 36 wins to 42 losses in simplest form. 36 to 42. You can also think of this as 36 over 42. So, we see that both are multiples of 6, so it's equal to 6 to 7. Are there units? Well, you could say 6 wins per 7 losses, but really, since these are going to be games, it's going to be 6 games over 7 games. So those units would cancel out. You could say their win to loss ratio was 6 to 7, though. That's fine. Okay, so let's express 1 meter to 32 centimeters in simplest form. Well, 1 meter is 100 centimeters to 32 centimeters. Now the centimeters cancel out because this would be 100 centimeters divided by 32 centimeters. So yeah, the centimeters cancel out. This is equal to, we see that both of these are multiples of 4, but 100 is not a multiple of 8, so we can only divide both by 4. So 25 to 8, or 25 over 8. Now what happens if we compare quantities with different types of units? Well, we get a rate, such as, say, kilometers per hour. Or if you're pumping a liquid, perhaps liters per second. Now a unit rate is a rate with a denominator of 1. Because rates generally do not cancel out the units, you must mark it with the appropriate units, such as 306 kilometers in 6 hours. Let's give this as a unit rate. That means 306 kilometers per 6 hours. You're going to end up with, hours can just be written as h, by the way. You're going to end up with 51 kilometers per hour. This is per 1 hour. Because we're finding the unit rate, we can just simply divide. Let's express each of these ratios in simplest form. 3 out of 9 students. Well, 3 to 9 is equal to 1 to 3, or 1/3. 8 passengers to 2 cars is equal to, up here, the units canceled out because it was 1 student per 3 students. So we don't put any units. But 8 passengers to 2 cars, that's equal to 4 passengers to 1 car. Or you could write 4 passengers per car if you want this to be a rate. Now, 18 red apples to 42 green apples is 18 apples to 42 apples is equal to, both of these are multiples of 6, so 3 to 7. 50 millimeters to 1 meter. Well, 1 meter is 1,000 millimeters, so it's 50 to 1,000 is equal to 1 to 20. And the units cancel out, even though initially we had different units. We had to do a conversion and they became the same unit, so they canceled each other out. Express each rate as a unit rate. 14 waves in 2 hours. Well, 14 waves over 2 hours is equal to 7 waves per hour. 200 miles in 5 hours. That's 200 miles over 5 hours, which is equal to 40 miles per hour. Although you often see this written as mph instead. Just like kilometers per hour would be kph. It's just that km/h and kph, you generally see more km/h, whereas miles per hour, in my recollections, you generally see more mph. Funny, isn't it? So, $49,812 in 12 months. That's $49800 per 12 months. Months is usually abbreviated to MO because MON is Monday and M is meters. So, no, we're not going to cheese this problem by going, oh, it's $49,008 per year. Because 12 months is 1 year. But no, that would be kind of cheesing the problem. And teachers would not be impressed. Because it's clear that this wants dollars per month. So let's say we divide. What do we get? Oh, 48,000. And then 1,800. 48,000, well, that gives us 4,000. And then 1,800, well, 1,200 would give us 100. And 1,800 would therefore be 150. So, $4,150 per month. The comma here is the thousands separator used in English-speaking countries for math or just number writing purposes. In some places, like the Francophone world, if I recall correctly, the comma is used as the decimal point. Yeah. How about the next question? 110 apples in 5 seconds. What are we doing here? Are we like dumping apples out of a bin or something? Or picking apples with machines? Maybe. So, 110 apples over 5 seconds is equal to 22 apples per second. So, that's how unit rates work. You just divide, and then you put the appropriate units. Proportional and non-proportional relationships. Two related quantities are proportional if they have a constant ratio between them. If they don't have a constant ratio between them, then they are not proportional, or non-proportional if you like single words. Example 1. The cost of one vinyl disc at a record store is $12. Yes, some people still like playing old vinyl records for whatever reason. Create a table to show the total cost for different numbers of discs. Is the total cost proportional to the number of discs purchased? Well, discs cost. Discs 0 cost 0. Discs 1 cost $12. Discs 2 cost 24. Discs 3 cost 36. Yeah, for every disc you buy, it costs $12 more. Therefore, the ratio is fixed the total cost is proportional to the number of discs purchased. So actually we should put what's proportional to what. Total cost is proportional to discs bought. Hurrah! So, example 2. The cost to rent a lane at a bowling alley is $9 per hour plus $4 for shoe rental. Create a table to show the total cost for each hour a bowling lane is rented if one person rents shoes. Is the total cost proportional to the number of hours rented? So the time in hours, if we have 0 hours, the cost is, well, $4 because you're renting the shoes. And if you have 1 hour, the cost is $4 for shoe rental plus $9 for the hour. So 13. If you have it for 2 hours, the cost is 18 plus 4, so 22. 3 hours, you have it for 27 plus 4, so 31. And for 4 hours, you have $40. Okay, then, so you're going to look for the ratio, which is dollars per hour, and 4 divided by 0 is undefined. $13 for 1 hour is $13 per hour. $22 for 2 hours is 11. Yeah, y'all see where this is going. So, is the total cost proportional to the number of hours rented? In other words, does the ratio stay the same? No. Cost non-proportional to hours rented. Okay. Let's say we use a table of values to explain our reasoning for these questions. A photo printer charges 20 cents per photo printed. Is the total cost proportional to the number of photos printed? Oh, God. Yeah, it's pretty obvious that because it's a fixed fee per photo printed with no base fee, the ratio of cost to number of photos is going to stay constant. Therefore, the cost will be proportional. But it says use a table of values, so we're going to use a table of values. Cost in dollars. Photos. 0, 1, 2, 3. That's enough. So 0, cost 0, 0.20, 0.40, and 0.60. Okay. Yeah, it's proportional. Proportional. Now, let's say we have a soccer club, which has 15 players for every team, with the exception of 2 teams that have 16 players each. Is the number of players proportional to the number of teams? How do you even use a table of values for this? Well, let's say, okay, teams and players. 0, 1, 2, 3. Okay, teams obviously have 0 players. 1 team, let's say that this is the 16-player team. Suppose 16-player teams are the first two teams. First two. Well, two teams, you have 32 players. However, with the third team, you end up with adding 15 players instead of 16. So you end up with 47 players. Now, this side you get +1 every time. +1, +1. Whereas on this side, well, this ends up being a +15, and this is a +16. So for every change in one variable, the other one should be the same if they are proportional to each other. So not proportional. As player increase per team added, not constant or inconstant if you like. Solving proportions. A proportion is an equation that tells you that two ratios are equivalent. To determine whether a pair of ratios forms a proportion, use cross multiplication, which at the current grade level may also be called cross product. Hint, cross product and dot product are completely separate things, and they are forms of multiplication once you get to studying vectors. So, you can also use cross multiplication to solve proportions. So determine whether the pair of ratios 20/24 and 12/18 forms a proportion. Well, cross multiply. Multiply. 20/18. So left side will end up being 20/18, which is equal to 360. And right side is equal to 12/24, which is equal to 288, because it's twice of 12 squared, which is twice of 144. Left side unequals right side. Therefore, ratios not a proportion, or not proportionate. Alright then, example 2. Solve 12/30 equals k/70. Well, you cross multiply, and you get 12 times 70 is equal to 30k. Right? Well, actually, you could have done a little bit of canceling before cross multiplying, so got rid of the zeros. And what do you get? You get 3k is equal to 12 times 7. You could also cancel the 3 and end up with just 4 times 7, but in this case we're just going to go right on ahead with that. And then divide. Okay, fine. So k is equal to 28. Okay, let's determine whether each pair of ratios form a proportion. Cross multiply. Five by 9 is equal to 45, and 10 by 12 is equal to 120. Unequal, not a proportion. I do believe up here in Canada, at least, we usually call this stuff equal ratios, like whether these ratios are equal. Like, we don't bother with the forms of proportion thing that much, at least as far as I can remember. But that was all so very long ago. So, cross multiply. Multiply. And you get 8 by 15 is equal to 120. 12 by 10 is equal to 120. Equal. So, proportionate. Perhaps thus would have been better there. Because so proportionate sounds, I don't know, kind of sarcastic or something. So, 4 over 7 versus 12 over 67. Well, cross multiply. Cross multiply. And we get 4 by 67, which is equal to 8. 268. And 7 times 12 is equal to 84. Unequal. Not proportionate. Okay. How about 18 over 24 versus 3 over 4? Well, you cross multiply. Yeah, this is why I prefer the simplify to simplest form choice for finding whether ratios are equal to each other, i.e. proportionate. Because if they are equal, they will simplify to the same simplest form. So 18 by 4 is equal to 72. 24 by 3 is equal to 72. Equal. Thus, proportionate. Proportionate. Okay then, let's say we want to solve some proportions. Well, we cross multiply. But before we cross multiply, we can cancel some things. So, 2, oh, hey, this is down to a 1 now. Wonderful. X equals 2. Yeah, that's why canceling before you multiply is so convenient. And you can cross this out to be a 1, this to be a 5. So R is equal to 3 by 5. Well, 1R, but whatever, same thing. R is equal to 15. And here, W over 6 is equal to 2.8 over 7. Now, it's not usual that you would do canceling for decimals. So, yeah, we'll let that slide. If you wanted to, you could totally cancel this to be a 0.4 over 1. But, well, personal choice. So 7W is equal to 6 times 2.8. W is therefore equal to 6 times 2.8 is 16.8 over 7. As you may have noticed, when you are cross multiplying, you don't actually need to cross multiply a denominator onto the variable if the variable is in a numerator. Because, well, at the end, you're going to end up dividing it anyway. 5 by 7 equals 2.4. Like here, if you're going to cross multiply, you might as well just go with 18 times 7 x equals 18 times 7 over 31. So 18 times 7 is 126 over 31, which means that x is equal to 4 times 31 is 124, so 4 and 2 over 31. Yeah, it's possible to have a fraction as a numerator or even as a denominator, so that's not a problem. It doesn't need to be a whole number. Problem-solving investigation. Draw a diagram. Ah yes, the obligatory problem-solving section. Drawing pictures can be useful if you don't have an idea where to begin. Draw a diagram to solve this problem. It takes a worker 4 minutes to stack 2 rows of 8 boxes in a warehouse. How long will it take to stack 8 rows of 8 boxes? Well, this is 4 minutes. So, your other rows of boxes are going to be plus 4 minutes, plus 4 minutes, and plus 4 minutes. Yeah. Lots of smiley faces with tongues out, I guess. And a staring face with no mouth. So, total 16 minutes. Yeah, well, how about we have these diagrams here? A car's gas tank holds 16 gallons. After filling it for 30 seconds, the tank contains 2.5 gallons. How many more seconds will it take to fill the tank? I mean, I suppose we could go for 16 gallons and 0, and then be like 2.5 would be about here. 2.5 gallons. And then be like, this is 30 seconds. If this, I don't know what, maybe this is for making this easier to visualize. Well, the mysteries of math textbooks never cease, such as eating a couple hundred watermelons at once. Or a few hundred candies for that matter. Yeah, what does he have left? Diabetes. Yes, okay, I'm sure you've seen the memes. So, a car's gas tank holds 16 gallons. After filling it for 30 seconds, the tank contains 2.5 gallons. How many more seconds will it take to fill the tank? Fill rate is 2.5 gallons per 30 seconds. Or you could give it as 12 seconds per gallon. 30 divided by 2.5 would be 12 seconds per gallon. You could say that it's 1/12 of a gallon per second, or 12 seconds per gallon. And how many gallons do you have left to go? You have 13.5 gallons left. So this is 13.5 gallons left. And this is already filled, so we should probably shade that. And at 12 seconds per gallon, that's 13.5 gallons times 12 seconds per gallon. The gallons cancel out, so you end up with seconds as your unit. 13.5 times 12 is what? Well, 12 times 12 is 144. And then you have a 1.5 times 12, which is 18. 144 plus 18 is 162 seconds. Now, our statement would be it would take 162 more seconds to fill the tank. It takes 96 tiles to fill a 2-foot by 3-foot rectangle. How many tiles would it take to fill a 6-foot by 6-foot rectangle? Yes, I said rectangle. Because guess what, guys? Squares are a type of rectangles. Okay, so what we have here is this. Yes, I know, they are so very equal. Yeah, my artistic skills are perhaps not the most brilliant thing known to man, I am aware. Thanks. Alright, so each of these is 96 tiles, 96 tiles, 96 tiles, 96 tiles, 96 tiles, and 96 tiles. So, total is equal to, we can clearly see that it's going to be 6 times 96, which means, well, this is 100 minus 4, so we get 600 minus 24, 576 tiles. Our statement would be, it would take 576 tiles to fill a 6-foot by 6-foot rectangle, or to fill this new rectangle. 4 juice cartons can fill 36 glasses of juice equally. How many juice cartons are needed to fill 126 glasses equally? Well, 126 is what? It's 10.5 dozens, or 21 groups of 6. 126 is equal to 21 groups of 6, or 7 groups of 18, and 4 juice cartons fill 2 groups of 18. So, how exactly do you diagram this? Like, are you supposed to draw 36 glasses or something? Huh. Well, okay, maybe we can just draw a group of 18 for cartons, for juice, okay, for juice, better. And then be like 7 groups of 18, okay, so 18. Sometimes I am truly baffled by North American math textbooks. Plus 4 plus half of 4. Okay, so we would be like, it takes 1, 2, 3. 3 times 4 is 12, plus 2, 14 juice cartons. Well, at least we avoided drawing 126 glasses. That would have been fun. Not. It takes 5 large shipping boxes to hold 120 boxes of an action figure. How many action figures would 8 large shipping boxes hold? Well, this is easy to diagram. 1, 2, 3, 4, 5. And then 24, 24, 24, 24, 24. So, plus 3 boxes means actually, yeah, let's just do it this way. 24, 24, 24, 24. Oh God. Yeah, well, we were required to do this by drawing diagrams. Eight times 24. So this is 192 action figures in 8 large shipping boxes of this type. Okay, similar polygons. 2 polygons are similar if their corresponding angles are congruent, as in equal, and their corresponding side measures are proportional, so they have the same ratio. Suppose triangle ABC below has side lengths 4, 6, and 8. Okay, so 4, 6, and 8. And DEF has 6, 9, and 12. Determine whether they are similar. Well, if all the angles had been labeled as equal, by the way, this is how you label angles as equal, or 2 lines, or 3 lines. I have also seen in some places you would put, say, 1 of these lines, or 2 of these lines, as the case may be. Okay? So conventions vary somewhat. Make sure you know how in your area it's noted. We know that equal lines would be, say, this versus this. So, determine whether they are similar. AB over DE is equal to 4 to 6, which is equal to 2 over 3. BC over EF is equal to 6 over 9, which is equal to 2 over 3. AC over DF is equal to 8 over 12, which is equal to 2 over 3. Okay, then we've shown that AB over DE is equal to BC over EF is equal to AC over DF, which is all equal to 2 over 3. So because of this, therefore, triangle ABC is similar to triangle DEF. Now, triangle ABC is similar to triangle DEF. Note, though, that sometimes you see this squiggle written the other way, like down first and then up. But A and D correspond. That's why they are written in this particular order. B and E correspond, and C and F correspond. When you're writing out similar shapes, the points correspond to the points in the other shape in the same position. Now, actually, we didn't know that these angles were equal until after we did this and proved by side, similarity that these two shapes were indeed similar. You can prove similarity by showing angle similarity. I mean, technically, you show all the angles are equal, and that will give you similar shapes for triangles. It doesn't work for, say, quadrilaterals. Why? Oh, hey guys, here we have a rhombus. Oh, let's keep all the angles the same. Stretch? Yeah, these are not going to be similar shapes. So, for triangles, you have angle. I mean, technically it's all three angles, but you only need to know two of them because the third one you can subtract. Realistically, even though for congruence you have stuff like angle, side angle, and side angle, which actually just converts to be the same thing, or side angle side. When you're talking about similarity, when two angles is enough for two triangles to be judged similar, two angles that match up, that are identical, that are equal, or are congruent, two angles are enough. So angle, side angle is not necessary. So what other methods do you have? Well, what if you only have one angle? Well, if you have one angle, it has to be between two sides where the ratio is the same to say that two triangles are similar. Okay, let's do another example. The rectangles below have the relationship of KLMN is similar to PQRS, and KL equals 8. KN equals 5, and PS equals 3. Now, the order the points are written out in is very important for what sides correspond to which. So PQ is what we're trying to find. PQ is unknown. Use a proportion. Well, because KLMN is similar to PQRS. Therefore, you could go KL over PQ, or just, okay, look, it's gonna make the rearrangements easier for PQ over KL to be equal to PS over KN. Alright, that means PQ, which is unknown, we can just keep it as PQ. And over KL, that means divided by 8, is equal to PS, which is 3, divided by 5. So PQ is equal to 24 over 5, or 4 and 4/5. Yeah, this is the proportion that would give us the length of line segment PQ, or you could say this is, and then we solved it. Well, okay. Let's do some exercises. Determine whether two rectangles of dimensions 15 by 6 and 4 by 11 are similar. Explain your reasoning. Well, here we happen to have two rectangles that we can use to consider this. 6 by 15 perhaps, and then 4 by 11. Well, consider the side ratios shows 6/4 versus 15/11. Well, 6/4 is equal to 3/2. 15/11 is not. Okay, what if we just cross multiply it instead? Cross multiply. Multiply. So 6/11 is equal to 66. 4/15 is equal to 60. Unequal. So 6/4 is unequal to 15/11. Okay then. Let's say we have two similar triangles below. Find each missing measure and then solve. Well, we see that the angles that correspond are the top ones, the ones on the left, and the ones on the bottom. Okay, so it's not like it flipped over or something. So the proportion is that x to 15, the ratio of x and 15, is equal to the ratio of 4 to 6 or 8 to 12. We only need one of them though. And then we cancel. This cancels to be a 5 and this cancels to be a 2 and cancels again to give a 2 up here. So x is equal to 10. 10 to 15 is 2/3, and 4 to 6 is 2/3. 8 to 12, same thing. Okay, so we found the missing measure. Speaking of measures, let's convert some. A unit ratio is a ratio in which the denominator is 1 and the numerator and denominator are equivalent. So that the value of the ratio is 1. 100% or 1,000 millimeters per meter are examples of, well, things we can consider to be unit ratios. So let's convert 2 3/4 meters to centimeters. The reason why I said things we can consider unit ratios is because 100% literally means 100 per 100. So 100 over 100. Yeah, that's 1. So, 2 3/4 meters to centimeters. Well, that's 2 3/4 meters times 100 centimeters per 1 meter. So the meters cancel out. 2 3/4 times 100 centimeters will leave us with 275 centimeters. Example 2. Convert 5962 milliliters to liters. Well, that's going to be 5962 milliliters. You can either use multiplication, in which case it's going to be 1 liter per 1,000 milliliters, or you could use divided by a unit ratio, i.e. 1,000 milliliters over 1 liter. And as we know, dividing by a fraction just means multiplying by the reciprocal. So, this is going to be 5.962 liters, because the milliliters cancel out. So that means we just divide by 1,000 and then put the unit liters at the end. Example 3. While driving today, Mr. Smith averaged a speed of 63 kilometers per hour. How fast is this in meters per second? Well, 63 kilometers per hour is kilometers per 1 hour. You need to multiply by how many meters per kilometer? So we need to divide by kilometers to cancel out the kilometers. Well, we need 1,000 meters per 1 kilometer. Okay, and then we multiply by, how do we cancel out the hours? And end up with per second. So per however many seconds, and we need hours on top. Well, the hours would cancel out with 1 hour over 3,600 seconds. Both of these, 1,000 meters over 1 kilometer, that's equal to 1. 1 hour divided by 3,600 seconds, that's equal to 1 because they are equal measures. So what happens here? We end up with, we can do some canceling. And 63 is 7 times 9. 7. And we cancel this out to be 4. So we end up with 70 meters over 4 seconds. Or 35 over 2 meters per second. What else could we write this as? Oh, we can write this as 17.5 meters per second. Now, exercises. Complete each conversion. Round to the nearest hundredth if necessary. 2 tons. Metric tons are used lowercase t. They use lowercase t instead of uppercase t for imperial tons. 2 tons. Each ton is 1,000 kilograms. So 2 tons is 2,000 kilograms. 5.5 liters is how many milliliters? 5.5 liters times 1,000 milliliters per liter is 5,500 milliliters. 4.75 meters, well, each meter is 1,000 millimeters, so 4,750 millimeters. 2,473 meters is how many kilometers? Well, it's 2.47 kilometers because it said nearest hundredth if necessary. So we put the approximation dot on top of the equal sign. Okay, let's say we have a restaurant. During the dinner rush, they cooked about 12 kilograms of spaghetti per hour. How many grams of spaghetti do they cook per second? Well, 12 kg per 1 hour multiplied by, first we need to convert the kilograms to grams, so 1,000 grams per 1 kilogram. So these units cancel. And then we need to convert hours to seconds. So actually it's convert per hour to per second, which means to get the hours to cancel, that's got to be in the numerator. And then in the denominator, we got per second. 3,600 seconds and 1 hour. So these cancel out. And we know that these can cancel out as well. And 36 cancels with 12 to just give you a 3, which means that they are cooking about because it said about 12 kilograms of spaghetti per hour, I'm going to say it's about 10 over 3 grams per second, which is 3 1/3 grams per second of spaghetti cooked. Converting square and cubic units of measure. Some of the units of area in the imperial or customary for Americans who don't want to acknowledge where it came from, although their system does differ from the typical imperial system a little bit in the size of some measurements. So the gallon, for example, varies. So it's always around 4 liters. Now the system, some of the units of area are square inches, square feet, square yards, or square miles. There are also other interesting units of area, such as the acre, but we won't get into that. Some of the units of area in the metric system are centimeters squared and meters squared. Let's convert 5 square yards to square feet. 1 yard is equal to 3 feet. 1 yard squared is equal to 9 feet squared. Well, I mean, technically it's 1 yard squared equals 3 feet squared, but 1 square yard is equal to 9 square feet. No math word games here, guys. Convert 5 square yards to square feet. Squared is equal to, well, 1 square yard is 9 square feet, so 5 is 45 square feet. Convert 2.5 square meters to square centimeters. Well, 2.5 meters squared. You can think of this as doing this, okay? 100 centimeters per meter, and then you square this so that the units cancel out properly, and that ends up giving you 2.5 meters squared times 10,000 centimeters squared over meters squared. So you cross these out, and you end up with 25,000 centimeters squared. Now, some of the units of volume in the customary system are cubic inches, cubic feet, cubic yards, and cubic miles. Some of the units of volume in the metric system are centimeters cubed and meters cubed. I mean, there's also milliliters, which are equal to centimeters cubed. There are liters, which are equal to decimeters cubed. And, well, let's just use the meters and centimeters for now. Convert 1,500 cubic centimeters to cubic meters. Well, 1,500 centimeters cubed. When you multiply, you're going to need to convert this to cubic meters, so meters should be on top. And, well, 1 meter specifically. How many centimeters is this? This is 100 centimeters. And you got to cube this so that the centimeters cubed, the units eliminate. So that means you're dealing with 1,500 times meter cubed over a million. 100 centimeters may be equal to 1 meter, but that means 10,000 square centimeters equals 1 square meter. And 1,000,000 cubic centimeters equals a cubic meter. So, when you multiply, you end up with, let's use decimals. Fun times. Okay, let's do some exercises. Complete each conversion. Round to the nearest hundredth if necessary. 6 centimeters squared is equal to how many millimeters squared? Well, 1 centimeter is 10 millimeters. So 1 square centimeter is 10 times 10, 100 square millimeters. So 600 millimeters squared. 0.25 meters squared is how many centimeters squared? Well, 1 meter is 100 centimeters. So 100 times 100 is 10,000. Or in this case, it's literally times 100 times 100. Why? Because 0.25 times 100, oh, 25. And then 2,500. Yeah, that makes the math easier. Okay. 234 centimeters cubed is equal to how many meters cubed? To go from centimeters cubed to meters cubed, it's 100 to the third. So 1 over 10 to the sixth. 1 over a million. Round to the nearest hundredths, if necessary. 234 divided by a million isn't going to give you a nearest hundredth. In fact, if you divide by the first 100, you get to 2.34. Okay, but then you divide by the second 100. Oh, the nearest hundredth is now 0.02. You divide by the third 100, it's gone. So it's approximately 0.00 meters cubed. This is why rounding is sometimes kind of inconvenient and why people like using scientific notation. 234 times 10 to the negative 6 is equal to 2.34 times 10 to the negative fourth. These are, of course, all in meters cubed. Okay, 2 meters cubed is equal to how many centimeters cubed? Well, we just said 1 cubic meter is equal to a million cubic centimeters. Or specifically, 100 to the third power, so 1 million cubic centimeters. So 2 million. Cubic centimeters. Of course, we can't really talk about ratios without talking about scale drawings and models, because one of the places you're most likely to use ratios in real life, well, scale diagrams of some sort, including, say, maps, is about it. So distances on a scale drawing or model are proportional to real-life distances, or the distances they represent, if you're representing something fictional. The scale is determined by the ratio of a given length on a drawing or model to its corresponding actual length. So for example, on a map you might see a scale of 1 to 30 million. That would mean 1 millimeter on this map is, take off 3 zeros for meters, take off another 3 for kilometers. So 1 millimeter on the map is 30 kilometers. Now, example 1. A designer made a scale drawing of a living room for one of her clients. The scale of the drawing is 1 inch equals 1 1/3 feet. On the drawing, the sofa is 6 inches long. Find the actual length of the sofa. The sofa is here in this particular drawing. So, 6 inches multiplied by 1 1/3 feet per 1 inch, because the inch is what we're trying to get rid of, leaves us with 6 times 1 1/3, or 6 times 4 over 3. So 8 feet. The actual length of the sofa, 8 feet long. Okay. Now let's find the scale factor for some scale drawings and models. Write the ratio given by the scale in simplest form. Find the scale factor for the drawing in example 1. Well, it was 1 inch equals 1 1/3 feet. So it was 1 inch to 1 1/3 feet, which means 1 inch to how many inches? 4/3 of 12 inches is 16 inches. So 1 inch to 16 inches. The scale factor is therefore 1 to 16. All right. Suppose a yard is illustrated with a scale of 1 centimeter equals 0.5 meters. The length of the patio is 4.5 centimeters in the drawing. Find the actual length. All right, then. That means 4.5 centimeters times 0.5 meters over 1 centimeter. And of course, the centimeters cancel out, so equals 2.25 meters. The actual distance between the water faucet and the pear tree is 11.2 meters. Find the corresponding distance on the drawing. 11.2 meters times, well, it's 1 centimeter per 0.5 meters. For every 0.5 meters, in reality, it's going to be 1 centimeter on the map. So that's going to be 1 over 0.5, also known as 2, times 11.2, so 22.4 centimeters on the drawing. Find the scale factor for the drawing. Well, the scale is 1 centimeter equals 0.5 meters. So 1 centimeter to 0.5 meters is equal to 1 centimeter to 50 centimeters, which is equal to 1 to 50, because it's amount in drawing to amount it's representing. Therefore, the scale is 1 to 50. It's at 1/50th scale. It's 1/50th as big as this thing it represents. Of course, if you're drawing something really small, you could have a scale factor that's like 100 to 1. You would say that's 100 times magnification. It makes something look 100 times bigger. Now for rates of change. So if you have two data points that are x1, y1 and x2, y2, then your rate of change between them, i.e. how far you change vertically per amount you change horizontally, is going to be the vertical change. So this is x2, y2 up here. And this is x1, y1 over here. The vertical change is going to be y2 minus y1. Okay? And the horizontal change is going to be x2 minus x1. The vertical change, you can think of it as a rise, although it can be negative. And you divide it by the run, the horizontal change. So the rate of change is per amount horizontally, how far are you moving vertically? Suppose you have a graph which shows Miss Gulliver's annual income between 2000 and 2006, and there's a straight line between the points 2003, 54,000, and 2006, 58,500. And the x-axis is in years, and the y-axis is in dollars per year. At what rate did her annual income increase? The rate of change is going to be rise over run. Yeah, we should start with that. Which is equal to y2 minus y1 over x2 minus x1. So y2 is 58,500 minus y1, 54,000 over x2, 2006 minus x1, which is 2003. So that's going to be 4,500 over 3. Wait a second. What are the units? Oh, y-axis is in dollars per year. And x-axis was in years. Okay, so it's going to be $1,500 per year, or dollars per year squared. Yes. When you find rates of change, sometimes you end up with some very funny units. Or, well, if you did physics, this is going to be perfectly normal because you're going to end up with meters per second. So the change in speed versus the change in time, well, or rather, change in velocity versus change in time, that's acceleration. So it's going to be meters per second squared. All right, let's use this graph for some exercises. The average daily wave height as measured by an ocean buoy over a 9-day period. Realistically, you're probably going to have another reading in the middle that's way high up because wave heights follow a sinusoidal function over time because of how spring tides and neap tides work. The tides are mainly caused by the moon, but the sun also has appreciable influence. So if the moon and the sun, the gravity both line up, you get the highest tides. So if the moon is a new moon, which is in the general direction of the sun, or a full moon, i.e. opposite the sun, you get the highest tides. If they're perpendicular, i.e. first or third quarter moon, you end up with relatively black tides. Of course, this also depends on location, since some inlets, such as the Bay of Fundy, have really high tides. Of course, they're still higher during spring tides when the moon and sun line up. So find the rate of change in the average daily wave height between day 1 and day 3. Rise over run is equal to, depending on teacher, you might still have to write y2 minus y1 over x2 minus x1, but this could also just substitute for that altogether, which would mean you can substitute in right away. Depending on the teacher, just be careful. So it's 12 minus 8 over 3 minus 1, which means you're dealing with 4 over 2. So 2 feet per day. That's the rate of change with the data we have. With more measurements, perhaps the data would be more curved, a smoother curve. So find the rate of change in the average daily wave height between days 3 and 7. Day 3 and day 7. So y2 minus y1 over x2 minus x1. y2 is 14 minus 12 over 7 minus 3. So we're talking 2 over 4. So 1/2 feet per day. Now find the rate of change in the average daily wave height between day 7 and day 9. Well then, that's still going to be y2 minus y1 over x2 minus x1. So y2 minus y1, that's going to be 11 minus 14 over 9 minus 7. Negative 3 over 2 equals negative 1.5. What are the units? Well, it's still feet per day. Constant rates of change. The slope of a line is the ratio of the rise or vertical change to the run or the horizontal change. So m is the symbol generally used for slope, and it's equal to rise over run. Find the rate of change of a line which passes through the points 1, 5, and 5, 22 if the x-axis represents seconds and the y-axis represents meters. Now, slope is usually just a number, but if you're told that the x-axis represents something and the y-axis represents something else, then yeah, you should have units. So, find the rate of change of a line which passes through these points. M equals rise over run. Or we could say it's y2 minus y1 over x2 minus x1. Which point you choose for x2 versus x1, it doesn't actually matter, as long as you choose one of them to be point 1 and the other one to be point 2. Because if you subtract and you get negative divided by negative, still positive at the end. Or if you get negative over positive instead of positive over negative, still negative at the end. So, y2, let's just give it in the order that it came in. 22 and 5. And the other one, y1, that's minus 5 and minus 1 for minus x1. So that's equal to 17 over 4. So 4 and 1/4. What are the units? Oh, x-axis represents seconds, y-axis represents meters. So it's meters divided by seconds. We could actually put that up here. Meters over 4 seconds. Okay, now let's say we have these points in a table that lie on a line. Find the rate of change in the line. Now that's plus 3, plus 2, plus 2, plus 2, and plus 2. And this is plus 3, plus 3, plus 3. So for every 3 days, 2 eggs are laid. Obviously, going back beyond day 0 makes a little bit of nonsense because you can't have negative 2 eggs, but well. Find the rate of change in the line. M is equal to rise over run. Now that means we're going to be finding eggs per day. So rise is 2 over 3. 2 eggs per 3 days. That's the increment by which the data point has moved between each day. Well, each listed day. So we can say that this is 2/3 eggs per day. This is the rate of change of the line. Of course, this line is a mathematical thing. Because I don't think you're going to show up on day 1 and be like, okay, so there are 2/3 of an egg laid into the nest. Yeah, no. Exercises. Find the rate of change for each line. What this means is that you mark down 2 points that happen to land on the coordinate grid, and you use m equals rise over run. This point up here is 4, 4. This point over here is 0, 1. So rise is 4 minus 1. Run is 4 minus 0. So it's 3 over 4. That is the rate of change for this line. M is equal to 3 over 4. Now for this line here, I know that these points are actually on the line. Normally, when you're given a diagram, you should not assume like this. Like, it's really, really, really not a good idea. But in this case, I just give them to you. Of course, if you're given a diagram and you're told to find a slope, at this grade level, if it looks like it crosses a coordinate grid crossing, yeah, it probably does. I mean, just make sure that you keep a close eye on whether it actually should cross. Because if you're told to just find it off a graph, you're just going to have to kind of assume that, yes, what you're seeing is what's actually true. M equals rise over run, and the rise is 4 minus -2 over the run, which is 4 minus 0. So 4 minus -2, that's 6 over 4. So M is equal to 1 1/2. Or 3 over 2. Like, people generally aren't that picky about writing your slopes if you write them as improper fractions, mixed fractions, whatever, as long as it gets the point across. The points given in each table lie on a line. Find the rate of change for the line. Look, if you know that they lie on a line, then you can really just start with the first and last points and go with that. But we want to make sure. So if we want to make sure, we got to take a look. +2, okay, +2, +2. Okay, no problem there. -1, -1, -1. So M equals rise over run. Or you can write this as change in y, delta y, over delta x. Change in x. Since y we know is -1 each time versus +2 for x, we end up with -1/2. So this one, +2, +1, and +3. Is this on a line? Well, let's check what happens with y. Oh, +3, +1.5, and +4.5. Okay, so it's in proportion with the change in x. M equals rise over run. And we can go with the rise being 8 minus negative 1 over 7 minus 1. So 8 plus 1 is 9, and 7 minus 1 is 6. So 3 over 2. This is perfectly fine for slopes. Improper fractions are okay. Right. If your teacher wants mixed fractions, please do so. So, for now, that's it on ratios and rates. So, see you next chapter.